Imagine you are a student choosing which class to attend. You have two great teachers, Tommy and Eric, but each has a different reputation when it comes to grade. Which class would you pick? If you decide to take class with Eric, you are not alone. But what if I told you that when we break this down further, the story changed completely? If we take a closer look at the data, we can see that both of Tommy's class have a higher average than Eric's class. In Eric's first class, there is 30% with an average of 85%, whereas in Tommy's first class, there is 10% with an average of 90%. In Eric's second class, there's 10% with an average of 65%, whereas in Tommy's class, there is 30% with an average of 70%. So if Tommy's student is doing better in both classes, why does Eric has a higher overall class average? In order to answer this question, we need to go back to 1899 where Carol Pearson first noticed that trends in smaller groups can disappear or even reverse when combined. Following Pearson's work in 1899, Yu built on this idea in 1903 by demonstrating how hidden variables within different groups can distort overall trends. His research revealed that failing to account for these underlying factors when combining data often leads to misleading conclusions, especially in social sciences and economics. Following Pearson and Yu, Edward Simpson advanced the discussion in 1951 by offering a formal mathematical treatment of how data aggregation can reverse observed trends. His analysis of interaction in contingency table demonstrated that the overall statistics might tell a different story than the individual groups. Although his work wasn't initially aimed at defining a paradox, it later laid the groundwork for what we now refer to as a Simpson paradox. So, what exactly is Simpson's paradox? Simpson's paradox is a statistical phenomenon where an association between two variables in a population emerge, disappear, or reverse when the population is divided into subpopulations. This counterintuitive result happened due to difference in group size or other structural imbalance in the data. To see this paradox in action, let's analyze a real-world example where combining separate categories lead to misleading conclusion. Let's look into this real-world example about the university admission. So at the first glance, it seems like female applicants have a higher acceptance rate in every department. Department A admit 80% of female applicants compared to 70% of male applicants. In Department B, females are accepted at a rate of 70%, while males are only accepted 60% of the time. And even in Department C, the female success rate of 60% is slightly higher than the male success rate of 57.1%. Surprisingly, when we calculate the overall acceptance rate, we find that male has a higher total acceptance rate of 69.2% compared to 67.5% for female. And this reversal is a classical example of the Simpson's paradox. The key lies in the distribution of applicants across department. A larger proportion of female applicants applied to the highly competitive Department C, where acceptance rates were lower overall. Meanwhile, more male applicants applied to departments with a higher acceptance rate, and this imbalance skewed the total result, leading to a misleading conclusion when looking at the combined data. This example shows why it is important to carefully examine how data is grouped before making a conclusion. Without breaking data into relevant subcategories, we might end up with an interpretation that contradicts to the real trends. In order to correctly interpreting the data, we should always asking ourselves these questions. How is the data grouped? Could a hidden factor be influencing the result? Are percentages telling the full story? By carefully analyzing data and consider all the possible influence, we can avoid misleading conclusion and make better informed decision. And thanks for watching. Keep questioning the number and you will never know what insight you might uncover.